Okay, thank you very much, Marine. So now I'm going to tell you something about the solution sets, how we define them, and a bit something also about the continuous commissioning tool. I would have loved to speak more about also the other tools that we develop, but unfortunately, due to time constraints, I will focus only on the continuous commissioning tool. So talking about the solution sets.
Werner, can you share your screen? You should go to quick start and share.
Oh, sorry. Okay, now you should see my screen.
Yes, perfect. Thank you.
Thank you. So about the solution sets, as I said before, we had some challenging objectives like the strong reduction of operative energy costs, 7 years of payback time, improving environmental quality, and that 75% of energy reduction that we mentioned before. So what is a solution set, first of all? The solution set is a combination of three main types of solution. Active solution developed within or analyzed and developed within the project, so the IBAN, smart integration of energy grid, electrical energy storage, refrigeration systems, and so on. Passive solution, where we have ventilative cooling, thermal zoning optimization, and so on. And conventional solution. We combine these three different categories. We combine technologies from these three different categories to have a solution set. The methodology for the selection of the solution set is the one that I try to represent with this chart. Basically, we start with data collection, then we move, starting from the top left, then we move to the building energy simulation modeling using the integrative modeling environment. So we made a detailed model of the shopping center. We use the 11 reference building that I showed you before. We validate the model using data coming from this building, and then we move to this other part where we analyze the inefficiencies in this type of buildings, and we define a first solution set for that specific building. We analyze the potential of energy saving on these solution sets, and we see if we manage to reach this 75% of primary energy reduction. If that was not the case, we move back to the solution set definition, and we start this iterative loop between solution set definition and analyzing the energy performance. Once we reach the 75% of energy reduction, we move to the economical analysis, and we analyze if we manage to reach the 7 years payback time. If that was not the case, we start another loop that goes from the economical analysis to the solution set definition, and so on, up to the point when we manage to respect all the boundaries all the goals we decided for this solution set definitions. Something about the assumptions we made. The years of reference was the 2016. We analyzed a period of 25 years. We had a discount factor that was either 0% or 8% in case the owner take money in loan to pay for the retrofit of the shopping center. We analyzed the electricity cost and also operational cost. And here on this table, I try to summarize all these assumptions that we made. The analysis worked in this way. Basically, we had the baseline that was defined by the energy model that we did and calibrate on the reference buildings. And then we start to apply the solution one after the other. Each solution was added to the previous one. So we had this solution number one that usually was the improvement of the lighting systems. Then we apply a second solution, then we apply a third solution, and then we analyze how the solutions interact between each other and which is the final energy savings. Because as Stefanos mentioned before, it's worth to point out that adding a solution to a previous one is not like that we add an energy saving to the previous one, but each solution has an interaction with the other one. So the interaction can be even stronger in terms of energy saving than a simple sum of the energy saving related with the two solutions taken singularly. So I'm going to show you an example that is the Katanet shopping center, which is a medium-sized shopping center located in Sicily. So we are talking about a region strongly cooling dominated. So talking about the building strongly cooling dominated. In this slide, I try to summarize something about this shopping center. Something about the actual energy consumption of Katanet. In these two graphs, we represent the energy consumption during the summer season and during the winter season. As you can see, ventilation has always a strong part in this shopping center. Here I'm talking about only about the common areas, which is the area where we were allowed to, in case to perform changes and so on. So talking about the common area, this is the energy consumption, how the energy consumption is divided between cooling, ventilation, appliances, and so on. As I said, ventilation is the main voice on this chart. The dashed line is the simulation of the energy consumption. As you can see, the energy simulation on the building performed quite well. The energy simulation managed to follow quite closely the real energy consumption of the building. So here are the solutions that we decide to study and to apply on this shopping center. First of all, as I said, we decided to apply an energy efficient lighting, where we managed to use more natural lighting, but also we study the application of energy efficient lighting, and we change also the schedule of the lighting. Second solution, we changed the heating and cooling set points. Before, the heating set point was 21 degree constant, and the cooling set point was 23 Celsius, when the temperature was around 26 Celsius outside. When the temperature outside starts to go up, they have this kind of a different set point, a set point that changes with the outdoor temperature. We propose to use 24 Celsius as a baseline for the cooling set points, and then up to the 27 Celsius. Then we have the third solution, where we propose to apply a ventilation on demand using some CO2 sensors in the building. So instead of using a fixed value of ventilation during the opening hours, we propose this ventilation that change based on the real need of the shopping center. Then we propose to apply natural ventilation, since there are several openings in with different orientations. That sounds a quite smart idea to apply. And then we have the fifth solution, that are the PV system. We propose to install 888 megawatts hour as a PV system. So here is the analysis of the energy saving potential. Here you can see the energy saving potential only for the common area. For the solution, apply one after the other. Actually, the solution are one added one after the other. So first of all, we propose the installation of lighting, energy efficient lighting. We managed to save 5%. Usually the number is much higher for the other reference buildings. In this case, it's only 5%, because this is a fairly new building. It was built in 2009. Then we propose the installation of the implementation of the heating and cooling set point, modified as I explained before, and we managed to reach the 12% energy saving. Then we apply on top of the other solution the demand control ventilation, and we reach the 37%. Then we apply also the natural ventilation on top of the other solution. We reached 39%. And then we have the photovoltaic installation. So at the end, we managed to have a 58% reduction in electricity consumption. In this case, we didn't reach the 75%. It is also one of the reasons because I decided to take this as an example, because I want to show you one of the most challenging reference building we analyzed. We reached 58%, but we have to remember that we did that working on a building that was built in 2009. So, of course, if the retrofit is applied on older buildings, the energy saving is much higher. But anyway, we reach almost 60% in working on a fairly new building. Something about the economical analysis. As you can see, we managed to have a payback time in 5.1 year with 0% as discounted. If we take account the discount, we have a payback time of 6.8 years. So even in this new building, we managed to propose a solution set that is capable to pay for its installation in less than 7 years. Now I want to move something on the continuous commissioning tool. The continuous commissioning tool has several goals. First of all, it's used for an overall supervision of the shopping mall, both from a comfort, energy, and economics point of view. This tool is made to analyze monitor data coming from the building monitoring system and compare them with the expected performance of the building. And also is made to verify, to check if there are faults, to make fault detection in the building. Which are the strengths of this tool? That is easy to be used, is simple to be replicated on other buildings, useful for building diagnostic using specific KPIs, and it's possible to compare the performance of the building in different periods. Something also that I would like to add about the key performance indicator is that we, in this continuous commissioning tool, a big part of the work was really about defining good key performance indicators. We managed to define new key performance indicators that take into account not only the energy consumption, which is a basic and always useful type of indicator, but also how well that energy has been used. So we managed to put together in the same indicator the goal for which the energy has been used. For example, if I'm using energy for heating and cooling the building, the scope is that for that energy is that I would like to keep good indoor thermal conditions. So we put in the same indicators indoor thermal comfort parameters and energy consumption, so that it was possible to evaluate is that energy used in an effective way or not. So that is one of the things that this new key performance indicator allow us to do. A quick look on the interface. This is the main, the main page of this interface. You have in the red square, we put a map with the demo cases, so you can see where the demo cases are located. And if you are an energy manager, you can find your building. You can click on your building and see some basic information about your building. Then there is this other square where you can see the first level of information about electricity consumption, for example, and where you can go and start to perform analysis on your building. And then there is the green square where you have all the different tabs for different in-depth analysis of the performance of the building. Something about key performance indicators. There is, for example, this key performance indicator on lighting. Here is you can see how it looks like, and all the tabs you can click to perform more in-depth analysis. Something interesting again is that probably you cannot read very well here, but this key performance indicator takes into account the energy used for lighting, but also the achieved value of visual comfort in the building, so that with a single parameter you can evaluate everything. You can evaluate the energy used and the effectiveness of that energy used in the building. So thank you. Sorry for that I rush a bit, but I try to stay in time.